There we go. Okay, it's 4 o'clock. Let's go and get started. I apologize for the little bit of a late start. There's a little bit of technical difficulties. Can everyone on Zoom hear me okay? Okay, good. Yeah, I think the camera was just kind of glitching out before, so I just had to restart the computer. Miraculously, that's still the answer to 90% of computer problems, is just to restart the computer. All right, so how's everyone doing today? All right, it's it's week 11. So yeah, this is when things start to get pretty tough. November's a pretty tough month to get through, just because we've been at this for a while. Luckily, Monday is a holiday, so hopefully your professors are aware of that. And so if you have a class on Monday, should be canceled. Of course, we have the benefit of not teaching on Monday, so we'll have 2 lectures next week. But just wanted to let you know that. Okay. All right, so the plan for today is we are going to be going over our next couple of algorithms. So we'll be going over coordinate search and pattern search. So these two algorithms are related to each other, so it kind of makes sense to go over them together. And hopefully we finish all of those up today. Okay. The other thing I wanted to talk about today is the final project. And so, some of you may have noticed this yesterday, but I did post the specifications for the final project. So that one is up. I don't really expect most people to start working on it until probably after the midterm exam. I think that's probably the next kind of order of business. But I did want to put it out there just to have it out there and let you know. Okay. You have a little bit over a month to work on the final project. So it is due on December 22nd. That is the Sunday after finals week. That's about as late as I can push it. But so you have over a month, but we'll be kind of working on it throughout this time. Okay. All right. So that's the first thing I want to go over today is to go over the final project, what's expected of you, what the final project's all going to be about, and then we'll hop back into coordinate search after that. Okay. All right. Any questions on anything before we get started for today? Okay. All right, so let's go ahead and let me go ahead and share my computer screen here. Okay, so if you go under the assignments tab of our Canvas site here, you'll see that the final project has been posted. Okay, so there's quite a few files here in the final project, and so I did want to take a chance to go over them. But the main file that we're going to go over is this one right here. Which are the specifications for the final project. Okay, so the final project for this semester is going to be what's called a truss optimization. Okay, so you'll be given this structure here. So this is a structure that is comprised completely of truss elements, and so your goal here is to optimize the lengths of each of these truss elements here to give an optimized design. Okay. So it's a nonlinear programming code, so you're not going to have access to the design variables in the objective function. So you're going to be unable to take any derivatives of the objective function. So you're going to be solving it just by taking evaluations. Okay. So this problem right here and kind of the way that I've structured the code is pretty similar to how a modern kind of optimization code would be written. Okay. And so we'll talk about that in a second. Okay, requirements. So actually, this figure here is a little bit of a misnomer here. So you are going to optimize this one, but I'm giving you a warm-up problem too. Okay, just because jumping straight into this optimization here is really challenging. So I want to make sure that I give you guys a good warm-up so that you can kind of test your codes and kind of get some confidence before kind of tackling this monster here. Okay. Okay, so the warm-up problem is this one. So it's a 2D truss. So there are 10 bars here. Okay. And the way that we're going to parameterize this truss here is we're going to go based off these 2 dimensions here. And so you're going to parameterize the height. We're going to modify the height of the entire structure, as well as the length of one segment here, L. Okay. So those are your two design variables. So it's going to be the length and the height of this structure. Okay. So on this structure, we're going to be applying loads, and so we're applying vertical loads P here that each have a magnitude of 10,000 pounds, and they're going to be applied on nodes 2 and 4. Okay. And so as a result of this loading here, this entire structure is going to dip. Okay. And so you'll be able to see that here. So in the code that I've given you for this final project, there's automatically kind of codes in there to plot the results and show you kind of the result of your design. Okay. So the way to kind of read this figure here is the black is kind of the original design, and then the purple is how the design looks like after you apply the loads. Okay. And so naturally, what you expect is that after you apply the loads P, both of those loads are acting in the negative Y direction. And so that's going to cause the entire structure to kind of dip. Okay. Okay. So for the warm-up problem here, you're only going to be responsible for optimizing 2 of these variables here. And actually, if you kind of play your cards a little bit right, you may be able to actually reduce it into a one-dimensional problem as well. Okay, so here are the constraints. And so we have 3 constraints that are going to be acting on this problem. Okay. The first constraint here is an equality constraint. And so, or excuse me, the second constraint is equality. The first constraint is an inequality constraint, which says that the total horizontal length of the structure cannot be shorter than 400 inches. Okay. The ratio of the height and the total horizontal length must be 0.4. Okay. So this second constraint here is an equality constraint because it's you can kind of read from the description here that it must be. Okay. So because we have an equality constraint here, that means we can work with direct substitution. Okay, so you can use direct substitution to reduce the dimensionality of the problem by 1. And the other constraint that you have is that the maximum force experienced by any element cannot exceed 300,000 pounds. Okay. All right, so we haven't gone over yet how to incorporate constraints into nonlinear programming. That's mostly what we're going to do after the midterm. That's good to kind of keep in mind. Right. Okay, so the objective function in this case is you're going to be minimizing the total amount of deflection of the structure. And so you're basically going to be minimizing, how much the structure is going to deform as a result of the load. Okay. So the function that I'm giving you here, it's going to solve the truss structure for you, and it's going to compute the XY deformations of each node in the structure. Okay. And so you're going to use that as your objective function for this part. So this first problem here is meant to be fairly straightforward. It's a straightforward objective function. It's a 2D problem. This is mostly just meant to kind of, get used to kind of how the codes are formatted, and then kind of to get some confidence in implementing these codes. Okay. Additionally, we have some upper and lower bounds for these variables, and so the length here will be constrained between the values of 100 inches and 500 inches. And the height will be constrained between the bounds of 80 inches and 400 inches. Okay. So that's the first problem there. In fact, if you go to the Canvas site, I actually already have one full solution for you implemented already using Monte Carlo. So Monte Carlo, you remember that was kind of the random method that we went over before. So this is kind of an implementation of that to solve this problem. Okay. Now, what that means that you can't use Monte Carlo for your project, or I should say, you can't use Monte Carlo by itself. You may be able to combine Monte Carlo with something else, but by itself you're not able to do that. Okay. Okay, so that's the warm-up problem. All right. Now the real problem here is this one right here, right? So we have a 25 bar truss. Okay, so there's 25 structural elements here. I'm not having you optimize all 25 elements here. That would be insanity. And so what I've done instead is I've broken up the structure into 6 main dimensions here. Okay. So basically the 6 dimensions here are going to be the height, the width, and the length of each segment or each portion of this structure. Okay. So I've broken up this structure into kind of a bottom section and a top section. And then for each of those sections, we're going to be defining kind of the width, the depth, and the height of those sections. Okay. And so in total, there's going to be 6 design variables in this problem, right? So we have a width, a depth, and a height, and then a width, a depth, and a height. So L1, L2, L3, L4, L5, and L6. Okay. All right. And then the loads that are being applied on this structure are going to be given by the following table. Okay. So, the loads are going to be fixed. And so the loads are not something that you're going to be optimizing over. Those are fixed for the problem. Your objective here is to optimize the values of these variables here when it's subjected to these loads. Okay. And so if you look at the structure, if you run it kind of in the base case and you apply these loads, you'll see that the truss actually deforms quite a bit. And so we have quite a bit of deformation right here. Okay. And so your objective here is to optimize the values of these variables to minimize that deformation. Okay. But what's also different in the second part here is that not only are you minimizing deformation, but you're also going to be minimizing the cost of production for the structure as well. Okay. Okay. So next thing we're going to go over is we have the constraints for this for the structure here, and so the total height must be 250 inches. Okay. And if you read this constraint a little bit carefully, you can see that this is also an equality constraint because the height is fixed. Okay. And so once again, you can use this equality constraint with direct substitution to reduce the dimensionality of the problem. Okay, so you go from 6 to 5, which is pretty big deal. All the other constraints here are inequality constraints. So for instance, the second constraint here is that the total base area, L1 times L2, must be at least 25% greater than the area of the middle base. Okay, so that's L4 squared. The width of the top element cannot exceed 75% of the width of the middle base. Okay. The maximum force experienced in each element cannot exceed 350,000. And additionally, this element at the top right here, that one is a little bit more fragile. So we have an additional constraint that the force in that element cannot exceed 200,000. And we also have a constraint that the height of the top section cannot exceed the height of the base. Okay. So quite a few more constraints here, but just so that you're aware of what to look. Okay, so our objective function for this is to minimize both the total amount of deformation as well as the material cost of construction. Okay, and so it's going to be up to you in this part of the project to come up with your own objective function that incorporates both of these factors. Okay, and I gave you some hints here to kind of help with it. Okay. So to compute the material cost, the truss elements that you are using for this construction has a material price of $125 per inch of material. Okay. So to compute the total cost of construction, you would just take 125 multiplied by the total length of all of the truss elements. Okay. And then for the deformations, you would compute it in the same way as the first one. Okay. Now, the thing you have to be careful of in this section of the project is that this is a multi-objective function. Okay, so we haven't really talked about that just yet. We'll talk about this in more detail kind of near the end, of course, after we go over constrained optimization. But basically, the idea is that when you have a multi-objective optimization, you can't just add their values together in your objective function, because these two things are going to have different units, right? The total deformation is usually given in inches, and the total construction cost is usually given in dollars, okay? And so adding them together is not going to be appropriate. And so one way that you can address this is you can scale each of these numbers by some kind of nominal value, okay? So for instance, if you scale the total cost by, let's say, 500,000, and you scale the total deformation by an amount of 0.1, and these numbers here are just examples, and so you can set these to be whatever you want. Then what you end up with is that the quantity in these parentheses here are dimensionless, right? And so basically the entries cancel out the signs, or cancel out the units. And then of course here we also have kind of the upper and lower bounds for each of these variables here. Okay. All right. Any questions on this part of the project here? Okay, good. Graduate problem. So if you are taking this course for graduate credit, either you're a grad student or you're an undergraduate taking for grad credit, you do have to do an extra part of the assignment. or extra part of the project. That's just a requirement for the school, right? And so the graduate project for you guys is to actually come up with your own optimization problem. Okay. So I've given you the codes here to basically create your own truss. Okay. And so what you're going to do is you're going to create your own truss structure and then optimize it and optimize its design. Okay. So I think so. There aren't too many of you grad students in the course, and so I think what I'll probably do is kind of meet with you each individually and kind of show you how the truss code works. Just because for everyone else in the class, it's a little bit too much information, and then you'll be able to design your own problem. Okay. Okay, so for all the problems, what you're going to do is I want you guys to compute the performance of your optimization algorithms, and so I want you to tell me, how many function evaluations and how long it takes for your algorithms to come up with an optimal solution. Okay. Ideally, whatever algorithm that you choose, it should outperform my Monte Carlo. Okay. And so that's kind of your benchmark is to do better than my codes. And you shouldn't have any problem with that because my codes are Monte Carlo, which is kind of the base one. But that's kind of your goal. Okay. All right. So I have a little bit extra information here about how to use the truss functions. I'm going to save that for probably after the midterm exam, just because I don't think anyone's going to start coding until Thanksgiving. So we'll kind of save that discussion for later. But I just wanted to kind of introduce the project to you in terms of what's going to be expected, and just so that you can kind of start thinking about it. Okay, we'll go over this a lot more kind of after the midterm exam. A lot more of this will make sense then because we haven't learned yet how to incorporate constraints into our nonlinear programming yet. So that'll be kind of the main subject after Thanksgiving. But I did want to at least give it to you guys. Just have you guys start thinking about it. And we can go from there. Oh, okay. One other thing. So team. So this is not a team project. So this is an individual project. So everyone is going to be writing their own code and everyone's going to be writing their own report. Right. With that said, with these kinds of projects where a lot of coding is going to be required of you, definitely feel free to talk to your classmates about that. Okay. Because I'm after Thanksgiving, I'm going to be doing my best to get around to everyone and help everyone with their codes. But I am only one person, and so if you're having some kind of technical issue with your code, some kind of syntax error or something like that, your best resource is probably to talk to your classmates first, and see if they're getting something similar, and maybe you guys can come together to office hours about that. But so definitely I'm supportive of you guys, talking to each other and helping each other out with their codes, but everyone has to write their own code and everyone has to write their own. Okay. So, I have kind of a suggested strategy here just because it's going to be a lot to code and a lot to do. We'll go over this in a bit more detail after the midterm exam, but there's kind of a best way to kind of approach this problem because otherwise there's kind of a little bit too much to do. All right, due date. And so due date, let's see. Like I mentioned before, the due date is going to be the very last Sunday after finals week. Okay. It's the last Sunday before Christmas too. So it's going to be due on Sunday, December 22nd by 11:59 p.m. That's as late as I can push it back. Normally I have it due on the Monday after finals week, but because this semester kind of we started so late, the Monday after finals week is December 23rd. And so if I have it due on midnight of that day, that means I have to finish all my grading on Christmas Eve and then, try to get the grades out before I see my family on Christmas. And so, this gives me just one extra day to do it. And so that's just to kind of help my mistake. Okay. All right, so that's the project. Any final questions about it before we jump back into the lecture? All right. All right, so all that's there for you. So definitely feel free, take a look at the example codes that I have for you because they're all going to be very useful to you, as you are going about doing the project. Okay, good. All right, and so with that said, all of the algorithms that we've been going over recently, Monte Carlo, random walk, today we're gonna go over coordinate search and pattern search. All of these are very viable methods to use for the final project. And so definitely good to, really, pick up these methods. In fact, I think coordinate search was probably the most popular method that was used in last year's project. So definitely a good one to know. All right, so let's go ahead and pick up where we left off. Coordinate search. Okay. So we just got finished talking about random walk, right? So random walk is kind of an interesting method in the sense that we're in order to optimize our design variables, random walk basically takes an approach where we start from a particular location and we take steps in random directions and hope that we find improvements. Okay. Now, random walk is effective. It does have linear convergence, and so it's a convergent method. It's good, which is good. But the randomness can be a little bit hard to control at times. So coordinate search kind of aims to take a similar approach to random walk, but instead of stepping randomly, we're instead going to be stepping in kind of predefined directions. Okay. So just like in random walk, we are going to be starting from a initial location. Okay. So part of this algorithm here is to start from a certain location, and we're going to be taking steps from this location. But just like I mentioned at the end of class on Tuesday, the way coordinate search varies from random walk is that coordinate search will take steps using only one variable at a time. And so the way the reason coordinate search gets its name is that if you were to visualize, how the search kind of process works, or how the search kind of process kind of progresses, it basically we're taking steps along the coordinate directions. All right. And so that was kind of the figure that we ended with last time, where we had kind of a two-dimensional plot. X1, X2. Let's say that we start our coordinate search from here. And let's say that the optimum that we're trying to achieve, is somewhere over here. So if we only change one variable at a time, we are basically, whenever we take a step, we're holding the other variable constant. Okay. So let's say that in step one of this algorithm, we are modifying the value of x1, but we keep x2 constant. Okay. And so what that looks like something like this, okay? So in this step right here, we kept x2 constant and modified only step 1. Or x1, excuse me. Okay. All right. And we move on to the next, we move on to the next step in the algorithm. So the next step in the algorithm, we're going to swap. And so we're going to hold x1 constant, and we're only going to modify x2. This step here, we kept x1 constant, modified x2. And then this process just kind of repeats. We just kind of, in this case, it's a two-dimensional problem, so we're just going to alternate between the two. Okay. And so the idea here is that, eventually, if you keep kind of doing this, eventually you're going to reach the optimum. Now, this is a search method, or this is a walk method, and so it kind of suffers from the same kind of issues as random walk. So last time someone brought up the issue of getting stuck in a local minima, this has the same problems. Okay. All of the kind of stepping methods all kind of have that same issue. Okay. Yeah, question.
Are the step sizes for x1 and x2 the same, or do we set them different?
They're not. And in fact, actually determining that step size is actually the most interesting part of this algorithm here. Yeah. So I would say compared to random walk. So in random walk, we kind of preset the step size and we kind of just lower it as the algorithm goes. This one we're gonna be a little bit more I guess intentional with how we choose the step size. So I would say compared to random walk, coordinate search is a little bit less susceptible to getting stuck, but only just a little bit, and so it still kind of runs into the same issue. Okay. The main benefit that you get here is that basically every iteration of this algorithm, we're only modifying one design variable at a time, and so essentially, what you can do is you can treat it as just a one-dimensional problem. Okay. And that's really cool because we've basically found a way to take our multi-dimensional problem, and this kind of scales to any dimension as well. So you can scale it up to 5 or 6 dimensions, which is conveniently the dimensionality of your final project, right? And so you can take a 5 or 6 dimensional problem and then just basically reduce it to a series of one-dimensional problems. Okay. And 1D problems, and if we're solving a 1D problem, that opens up a lot more possibilities for us. Because the last 2 weeks before this, we were just talking about just 1D problems. Okay? 1D problems are just really nice, and so if we can use those techniques here, that's going to be helpful. All right. So that's the idea, And so, unlike Monte Carlo and unlike random walk, we've completely removed randomness from this, from the equation here, okay? And so if you run coordinate search on a particular problem, it should take the same path to the optimum every single time because there's no randomness involved. Okay, so let's go over the algorithm. Or first, any questions on just kind of the idea of coordinate search? Okay. All right, so this is the coordinate search algorithm. This is kind of like a pseudocode too, a little bit, and so we'll kind of treat it as such. Okay. Okay, so just like random walk, we can't start this algorithm without some initial point. Okay, so we need to choose a starting point. Right, so and also just like random walk, the performance of this algorithm is going to change depending on your starting point. Okay. So actually, one strategy for not getting stuck is that people will run coordinate search with multiple different starting points and kind of see, if they end up with the same result. Okay. Okay. Step two. Step two is to set the search direction. In other words, the search direction is merely just going to be, you're going to choose which design variable to modify first. Okay. So one way that you can kind of visualize the search direction, if we're kind of using the same kind of terminology that we use in random walk, the search direction here are just going to be unit vectors in each of the coordinate directions. For example, so normally, normally when you do coordinate search, the first variable that you're going to change is just whatever the first one on the list is. Okay. So let's say for a three-dimensional problem. Okay. Your first search direction is going to be the first design variable. And so your first search direction would look something like that. So you have one, you put a one in the direction that you want to change first, okay? Or the design variable you want to change first, and then zeros for the other ones. Okay. Your second search direction would be, we're going to modify the second variable, but leave the first two fixed. 3, 0, 0. So sometimes it's useful to think of the search directions like this, especially if you're using the visual kind of interpretation of coordinate search. But another way is just to simply just say, like, I'm going to modify the first variable first, second variable third variable. Okay. Step 3. So step 3 of the algorithm is that we are going to take a step in whatever direction that we chose, but we need to compute the appropriate step length. In other words, what we're determining in this step is how much how much should we change our design variable, in this part of the algorithm? Okay. So this is where the algorithm kind of gets interesting. This is kind of where you can kind of modify it as well. Okay. Choosing a step length is actually not that easy of a problem. Okay? Because what we want, ideally, is we want to choose a step length that's going to lead to the best improvement of our objective function possible. Keeping in mind that for a given design variable, okay, we're going to be doing this formula here. Okay. So basically, in our objective function, you're going to be replacing the design variable with this formula here. Okay. So this step is pretty important because we're not just making a random change to the design variable. We're changing it from our current location. Okay. And so, for example, let's say that we have a two-dimensional problem. So let's say we have f of x1 and x2 is equal to x1 squared minus 3x1 x2 plus x2 squared. All right. And so let's say that we want to, we're kind of in the middle of a coordinate search algorithm, and we want to make a change to x1, leaving x2 constant. Okay. So we're going to take a step in the x1 direction. And so what we're going to do is we're going to replace x1 with x1 plus lambda. Okay. So now our objective function is f of x1 plus lambda, x2 equal to x1 plus lambda squared minus 3 times x1 plus lambda x2 plus x2 squared. Okay. So that's what it means to take a step in that direction. Okay, so you're basically just replacing the design variable that you're changing with the design variable plus the step. Okay. Okay. So now how do we choose the step length, right? So this is how we apply the step, but this doesn't tell us how to choose that step length lambda, okay? So to choose the value of lambda, we are basically running a one-dimensional optimization, right? So if you look at this problem here, you look at this objective function, okay? And if you assume for a second that we know that x2 is going to be held constant, okay? And because we replaced by this, we replaced x1 by the stepping function here, x1 is going to remain constant as well, okay? So what if we take this objective function and we solve it as a one-dimensional optimization where we are solving for the value of lambda that leads to the best improved? Let's treat this as a 1D optimization. On the variable. So there's lots of ways that we can do this. So we have a whole gamut of one-dimensional methods available to us. And actually, in this particular problem, we actually have our classical methods as well, right? So this is probably one of the only places where we can kind of blend our classical methods together with our nonlinear programming, just because we just have the objective function here. Okay? So for now, I'm going to show you how to do this with the classical methods. But later on, we'll do an example where we do it with a true kind of nonlinear sense. Okay. So if we use classical methods, the way we're going to solve this is we're going to take the derivative of the objective function with respect to the step length and set it equal to 0. Okay. Then we're going to use this equation and solve it for lambda. Okay. So that's one way that you can determine the step length. Okay. But just note that there are other methods to determine the step length as well. Using the classical methods in this case is kind of like cheating a little bit. Remember, we're not supposed to be using derivatives. So we'll go over a bit later how to do that. But just the fastest way to get the step length, at least for now, just learning, is to take the derivatives. Okay, but we'll go over methods to avoid that. Okay. So once you compute the step length, however you compute it, the next step in coordinate search is to actually apply that step. So let's take a step in that direction. And then that completes one iteration of coordinate search. Okay, and then after that, the next step is just basically just repeat. So step 5 here is return to step 2. But of course, you can't just keep taking steps in the same coordinate. So we're going to return to step 2 and but choose a different direction. Okay, so you're just going to keep repeating that over and over again until you reach convergence. And so how do we know when the algorithm converges? We know the algorithm converges when the step length computed in step 3 is close to 0, okay? And so what that basically tells us is that, if we can't, we can't take any more steps in this direction to lead to an improvement. All right, any questions on the algorithm before we do a quick example?
Is step 5 just a is that when you choose a variable?
Or excuse me, sorry, can you say that again?
Is step 5 when you manipulate the other design variable?
Exactly, yeah. So step 5 is to go back to step 2. So step 2 is up here. So we just kind of executed this algorithm for maybe the first direction here. And so when you get to step 5, we're going to repeat that all for the second direction here. And then do it again, and you come up and you do this one again. And then you cycle back and you go back to the first direction, second direction, third direction. Yeah, so you just kind of cycle through the directions just like that.
Okay, thank you.
Question?
Would there ever be a case where there's an issue like one of them, it's kind of converged on the right value that you move in a different direction, you'd get a worse result, but the other ones still need to be optimized?
Oh, yes. So yeah, I should be a bit more clear. So step 6, when you check for convergence, it's when all 3 directions or all the directions that you get kind of a very small step size. Yeah. Because yeah, that is very possible. So if you hit, maybe not a pit, but maybe you hit a wall and you have to kind of continue along that wall to reach through to the other. Okay, so let's do an example, a full example this time. And I'll actually kind of execute this by hand a little bit first before jumping in the code, just so that you can kind of see how the algorithm works. Okay. Okay, so for this example, we want to minimize the following function. It's the same function that we've been working with Monte Carlo and random walk. So it's f of x1 and x2 is equal to x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay. So let's start from 0, 0. And let's use coordinate search. Okay. So we have our objective function here. We have 2 design variables, just x1, x2. And so we're going to use coordinate search to find the optimum. Okay. So we're only going to change one variable at a time, and we're going to leave the other one constant. Okay. So let's start by searching in the x1 direction. Okay. And so we're going to write our objective function, but we're going to put everywhere we see x1, we're going to replace it with x1 plus lambda. We have f of x1 plus lambda, x2 is equal to x1 plus lambda minus x2 plus 2 times x1 plus lambda squared plus 2 times x1 plus lambda x2 plus x2 squared. Okay. Okay. So let's take the derivative of this. And so we are kind of gifted a situation here where we can use the classical methods. Okay. So let's determine the best step size. So let's take the derivative of f with respect to lambda. Okay. And so if we take this derivative, we end up with 1 plus 4 times x1 plus lambda plus, let's see, 2x2. And the x2 squared is going to equal 0. We all set all that equal to 0. Okay. Okay. So now that we have this expression here, let's go ahead and solve it for lambda. And so if we kind of, I'm going to go a bit fast here, so I want to get through this. Okay. So if we solve for lambda, we end up with a minus 1/4 multiplied by 1 plus 2x2 minus x1. Okay. All right. So this right here, this is the optimal step size. Whenever we're taking a step in the x1 direction. Okay. So you're actually going to see this formula implemented in the code as well. Okay. Notice how this formula here actually depends on the current location of x1 and x2. Okay. So that means as the algorithm goes, this step length is going to change depending on the values for x1 and x2. Okay. So for instance, in the first iteration of the algorithm, remember we're starting from 0, 0. Okay. So in the first iteration, x1 is equal to 0 and x2 is equal to 0. Okay. That means lambda here is going to be equal to minus 1/4 times 1 plus 2 times 0 minus 0. Okay. So that means in step 1, the optimal step direction is actually to go backwards. So it's actually to go, reduce the value for x1, and we're going to reduce it by an amount of minus 1/4. Okay. Okay. All right, so now let's do the same thing in the x2 direction. So once again, I'm going to plug in into the objective function, but this time I'm going to plug in x2 plus lambda. Okay. We have f of x1 comma x2 plus lambda equal to, we have x1 minus x2 plus lambda plus 2x1 squared plus 2x1 x2 plus lambda plus x2 plus lambda squared. All right, so once again, we're going to take the derivative of this function here with respect to lambda. And so if we do that, we get -1 plus 2x1 plus 2x1 plus x2 x1 plus, or sorry, to be 2x1, and the second one is 2 times x2 plus lambda. Couldn't really read my own writing. Okay. Set all that equals 0. Right. And just like we did with the x1 direction, let's solve for lambda. Yeah, lambda is equal to a positive 1/2 multiplied by 1 minus 2x1 minus x2. Okay. So this formula here, this gives us the optimal step length whenever we're stepping in the x2 direction. Okay. And so if we apply this to our, we just kind of compute the first iteration by hand, okay? So remember, our starting point for this algorithm was 0, 0, right? So that means x1 is equal to 0, x2 is equal to 0. But we've already taken a step in the x1 direction, okay? So we've already taken a step of -1/4 in the x1 direction. Okay. And so we plug that in here. X2 is still equal to 0, okay? And so we plug that in there, we get lambda is equal to 1/2 multiplied by 1 minus 2 times -1/4, okay? Minus 0, okay? Okay. And so if we plug in for that, we kind of evaluate this, we get lambda is equal to, we have a 2 times -1/4, so it's a -1/2. 1 minus -1/2, that's 3/4. Or 3/2, and multiply by 1/2, we get a positive 3/4. Okay. So after one iteration, we've taken our step of -1/4 in the x1 direction. Now we're going to take a step of plus 3/4 in the x2 direction. We have x1 is equal to -1/4, and x2 is equal to positive 3/4. Okay. Right, and then we're going to keep going. So of course, that's not the end. That's just the end of the first iteration. And so you just keep continuing this algorithm, just go back and plug in how much you're going to step in x1, how much you're going to step in x2, and you keep doing this until you reach convergence. All right, any questions on how we obtain this result here? Okay, good. All right, so let's go over the code. Okay, so I do have an example code for this as well. Actually, let me go ahead and switch to my computer here. And once again, I forgot to open up MATLAB. I said on Tuesday that I wouldn't do this, but I did it again. Go ahead and download the, while that's starting up, we'll go ahead and download the coordinate search code. So the coordinate search code you can see here is U_NLP underscore example 3 underscore coordinate search. So let me go ahead and download this.
Dr. Tran?
Yeah.
Do we not actually evaluate the objective function after this?
So in this case, we kind of cheated a little bit because we're using the classical method. So we're taking derivatives. So the objective function showed up when we took derivatives for the step. Okay. So it's kind of cheating a little bit. We're using derivatives here, but after this, I'll show you how to run this algorithm without taking derivatives.
Okay.
And so it'll be kind of the same thing as like the Newton method, the Newton-Raphson method, and the quasi-Newton. It's a little bit different than that implementation, but same idea. Okay, MATLAB is still starting up. Okay. All right, so let's go ahead and open up the script that we just downloaded here. Okay. So this is our coordinate search algorithm. So you can see it's pretty short. It's pretty short in this case just because we know what direction that we're stepping in. Okay. Okay. And actually I need to modify this algorithm a little bit. Okay, but you can see here that we're basically implementing everything that we just talked about. Okay. So we have our objective function here. So this objective function is the same one that we just went over in class. We have our initial guess here. Okay, so it's 0, 0. And then from there, we start stepping. Okay. All right. So since we use the classical method to compute the optimal step length, we know what that is already. So we just implement that formula straight into the code here. Okay. Actually, I need to modify this a little bit. So, earlier in class today, someone asked the question of, what if you reach convergence in one direction, but not the other direction? And so you want to make sure that you step adequately in all the directions. So if I were to modify this, I would basically move this one to the end. And we're going to move this one to the end as well. Yeah, sorry about that. But the main part of the algorithm is kind of right here. So this is exactly kind of what we just did in the class. So we have a formula here to compute the step length in the x1 direction. So you can see here this matches up exactly what we had in the code. So you have -1,4 plus 1 plus x2 minus x1. And then we apply that step in the x1 direction. And then we compute the step length in x2 using the other formula that we came up with, which is 1/2 times 1 minus 2 x1 minus x2. We take a step in the x2 direction. Okay. And then finally, we check for convergence. And so if we, if both the step lengths are less than the threshold, okay, and so basically if both the step lengths are basically 0, then we can exit the algorithm. Okay. Another way that the algorithm can converge is if you can see here we have a for loop, and so we just kind of let the for loop just kind of finish from there. Okay. All right. So let me go ahead and run the code. And you'll see it runs very quickly. And you can see that we end up with our optimal values here. So the optimal value for x1 is -1, and the optimal value for x2 is 1.5. Okay. Okay, so actually, let me just comment this out. Okay, so this is just kind of pure coordinate search here. So stepping in one direction, determine the step length, stepping in the other direction, determine the step length, and we just run it. Okay. We end up with the same result. Okay, so that code is available to you online, so you guys can definitely use it. Coordinate search was a very popular algorithm for the final project, and this is part of the reason why is that it's conceptually very kind of straightforward to do. Okay, but next let's talk about an improvement over coordinate search, which is pattern search. And through pattern searching, we'll also talk about how do you modify this method, for cases where you can't take the derivative of the objective function, which is kind of our whole spiel with this section. Okay, so of course we only have about 10 minutes left, and so I think I'll just kind of introduce the idea of pattern search, and then we'll pick this up on Tuesday. Okay, so let's go over pattern search. Okay. So coordinate search is great. So coordinate search is a very kind of straightforward, it's a very intuitive algorithm. And even if you knew absolutely nothing about optimization, that may be the approach that you would take anyway, to optimize the result, right? So you just kind of change one variable at a time. Okay, so that's the whole thing. Okay? Pattern search was designed to be an improvement over coordinate search. Because the thing that can happen in coordinate search is that it can be a little bit slow, right? And so when you're only changing one variable at a time, you could, eventually you're gonna approach the optimum, but it's gonna do so in kind of a very slow way because you're only changing one variable at a time. Okay? And so in problems where you have kind of multiple variables, and so 5, 6, 7, 8 variables, changing only one at a time, for one full iteration is going to take, quite a long time. And in optimization, speed is the name of the game. So if you can design an algorithm that's going to work faster, that's always going to be better. Okay. So the idea with coordinate search, or the idea with pattern search, is this, right? And so when you do coordinate search, and you basically you take steps in each coordinate direction, what people start to notice is that, this kind of traces out a pattern. With one full iteration of coordinate search. And by full iteration, what I mean is that, we've taken a step in every coordinate direction. So we've taken a step for every design variable. So after you make one step in each direction, a pattern starts to, emerge that we can kind of take advantage of. Okay. Let me kind of illustrate this to you just so that you can see. All right, so we have our usual kind of two-dimensional kind of design space here, just because it's the easiest one to kind of illustrate. Okay. And so let's say that we're starting our coordinate search from here, and we do one full iteration, and so we end up right here. We made a change in step 1, we made a change in step 2, and then we made a change in x1, we made a change in x2, and we end up in that location right there. Okay. Now the way that we arrived here is we took two separate steps, right? So we took a step in the x1 direction, we took a step in the x2 direction. A faster way to get here is if we took one step, right? So instead of taking these two steps, what if we just took one step and we just went straight here, okay? And so, yeah, that would be great. And so, you know, we took half the amount of steps to get here, okay? The problem is, you know, when you take kind of an oblique step like this, you're changing more than one design variable at a time. Okay. And so suddenly, you know, it becomes a lot more complicated to determine your step. Okay. Okay. But, you know, after we took our two coordinate steps, you know, we can kind of draw this kind of oblique vector. Okay. So from our first two coordinate steps, from our first two coordinate steps, we start to see that if we move in this orange vector direction, you know, that's going to be the general direction of where the optimum is, or at least that's the logic. Right. So if we know this direction, right? So if there was any way that we can find out this pattern direction, then we should just take steps in that direction, because that will get us closer to the optimum faster than if we just do x1, x2, x1, and x2. Okay. So this direction here, the orange one, we call this the pattern direction. And so the way pattern search works is that, you know, once you're able to determine a pattern direction, pattern search is just kind of a it's just the same thing as coordinate search, but we add one additional step. And so that additional step is to take a step in that pattern direction after you do each of the coordinate steps. Okay. Okay. So that's all it is. And so pattern step is, you know, the code is mostly going to be the same as coordinate search. The only difference is that, you know, we're going to take an additional step in that pattern. Okay. So before we go today, let me kind of illustrate to you just kind of what this looks like. Right. And so pattern search will start the exact same way as coordinate search. And so we're going to start with an initial point here. We're going to take a step in the x1 direction, take a step 2 in the x2 direction. Okay. That's our first step. This is our second step. Okay. And then from here, you know, we can see that we have a pattern that's emerging. Okay, so if you draw a vector that goes from your starting point to your ending point, that right there is your pattern direction. So your third step is going to be in the same direction here for a given, you know, for a given amount. Okay, so this is our third step here. Our third step is going to be a move in the pattern direction. And then from there, we resume coordinate search. And so coordinate search, you know, maybe in this iteration, we only step a small amount in the X direction. We step a larger amount in the X2 direction. Okay, so this is step 4, this is step 5. Once again, we determine the pattern direction from here. We draw that direction up here, okay? Just like that. Okay. And so the idea with pattern search is that, you know, by taking advantage of these patterns that emerge, we're going to be able to reach the optimum a lot sooner. Okay. And pattern search also has the benefit of, you know, because you're kind of moving in these kind of oblique directions, it kind of helps to avoid some pitfalls. It helps to avoid getting stuck. It still gets stuck. It doesn't fix the issue, but it's a little bit better at getting unstuck compared to random walk and coordinate search. Okay. All right. Any final questions on this before we wrap it up? Okay. All right. So that's all we got time for today. And so when we come back on Tuesday, we'll wrap up pattern search. We'll talk about an alternate method for computing a step length. That's typically done in practice. And then we'll move on to kind of the coup de grace of this section, which is called a Nelder-Mead optimization. Okay. So Nelder-Mead is probably going to take us the whole week to explain. It's a pretty complicated algorithm. But yeah, so thank you guys for coming today. Hope you guys have a good long weekend, and I will see you guys on Tuesday.
Oh, Dr. Chen, I was wondering, how do they evaluate how well new methods converge when they're so dependent on like age start?
Oh yeah, no, that's a great question. So there's a lot of benchmarks that are run typically for these problems. One very popular benchmark that's online is called the Rosenbrock problem. So they basically run the algorithm on these benchmarks. So of course, you know, different algorithms are going to perform better on different benchmarks, of course, dependent on different starting conditions too. But it's all pretty standardized.
Okay.
Yeah, so you basically run the algorithm for these benchmarks, and then you kind of see how quickly it converges. Also, you know, whenever someone comes up with an algorithm, they usually publish it in a paper, and they usually test it on an optimization problem of their own. And so, you know, when you kind of craft the problem, you kind of modify it to converge better too. So, you know, there's nothing, you know, for these methods, you know, these are pretty well tested. So these convergence rates are pretty well, you know, they're pretty well accepted. But for a new algorithm, you have to kind of read between the lines a little bit. So someone said, you know, I came up with the Tran optimization algorithm. You kind of have to see like, okay, how did he actually test it? Did he actually test it with benchmarks? Does it only work for his specific problem? So there's no optimization police to say that you can't claim this, but you know, so it's kind of a fairly kind of
Okay.
Yeah.
Thank you.
Yeah.
I was curious because I was like, wait a minute, that's very different than like the, you know, Monte Carlo. You go all over the place when
Yeah.
it changes based on where you start.
Yeah.
That makes sense.
Yep.
Cool. Alrighty then. Oh, also, I still have